Okay, in this video, we're going to work with not counting principles, but we're going to work with sequences and series. All right, so we're going to be working with sequences and series in this video. Okay, so the first one, we say find the sum of the infinite series, and it gives us a particular series. And so when we look at this, we can look to see if we have a common difference. We can say, okay, well, what is negative 12 minus 18? Right, and that would be negative 30. And what is 8 minus negative 12? That would be positive 20. So we don't have a common difference. So we would say we are not arithmetic. Right? And then we look to see if we have a common ratio. So negative 12 divided by 18, that would be, if I simplify this to be, what would that be? Negative 2/3. And if I consider 8 divided by negative 12, that's also negative 2/3. So I have a common ratio. So therefore, we would say that we are geometric with my common ratio being negative 2/3. Well, what does that mean for me? That means that I have a sum for my infinite series, right? That the sum for my infinite series, if I know I'm geometric, is going to be my first term, in this case 18, divided by 1 minus my ratio, so it would be 1 minus negative 2/3. Right, so that's going to give me 18, and I can think of 1 as a 3 over 3, so that's going to be 3 over 3 plus 2 over 3, so that's 18 divided by 5/3, which then would mean that my infinite sum would be 18 times 3 divided by 5. And if I do 18 times 3, that's going to give me what, 24. So that would give me a 54 divided by 5. So that's going to be my infinite sum of 18 minus 12 plus 8 going on. Okay. Then we look at B. Here's a different series, and we say find the sum if possible, right? And over here, this shouldn't have an equal sign, right? That should be just a plus. So find the sum if possible. So we look to see, do I have a common ratio? So for B, consider the common ratio. So 4 root 2 divided by 8 is the same thing as root 2 over 2. Right? And 4 divided by 4 root 2 is the same as 1 over root 2. But I know that if I rationalize that denominator, that's root 2 over 2. So therefore, my common ratio is root 2 over 2. Let's slide that up so that we can see. Okay, well, where do we go from here? Since the magnitude of that common ratio is less than 1, and how do I know it's less than 1? Well, I know the square root of 2 is less than 2. Divided by 2 will give me a fraction less than 1. So since the magnitude is less than 1, the infinite sum exists. Infinite sum. Or we can say converges. Let's use that phrasing instead. Right, that our infinite sum converges. And we're going to use the same formula for the infinite sum of this geometric progression, where that sum to infinity is going to be my first term. Right, for this particular problem, the first term was 8. So the sum is going to be 8 divided by 1 minus my ratio, and my ratio there was root 2 over 2. So similar to what we did in the earlier problem, this is the same as 2 over 2 minus root 2 over 2. So what I would have is 16 divided by 2 minus root 2. And that is perfectly okay to leave as your solution. That is our exact value. Okay. Next, we come and we say, okay, well, what about this one? What's going to be the sum here? Well, for this one, if we look, we see, hey, I'm adding 4 and I'm adding 4. So I'm adding the same thing each time, which means I'm arithmetic. So for C, I have an arithmetic progression. All right, for C, I have an arithmetic progression with a first term equaling 7, an nth term equaling 99, and a common difference equaling 4. Now, the sum of the first n terms of an arithmetic progression is going to be given by the number of terms I have over 2 multiplied by the first term plus the last term. Well, for us, that means that we just need to figure out how many terms I have. How many terms are there going from 7 to 99? Well, what do I know? I know that that nth term is going to be 7 plus my common difference times n minus 1, and that nth term here is 99. So, looking to solve, I can say that 4n minus 4 needs to equal 99 minus 7, so that would be 92. And so then that means that 4n needs to equal 96. I know that 4 times 25 equals 100. And that would mean that n must therefore be equal to 24. So what does that tell me? That tells me that I have 24 terms going from 7 to 99. Okay, so now I know that the sum of the first n terms is going to be the sum of 24 terms, which is going to be 24 over 2 multiplied by 7 plus 99, which would be 12 multiplied by, let's see here, 7 plus 99 would be 106, so 12 multiplied by 106. And if I don't have a calculator, I can still calculate this value, because that's going to be like saying 12 times 100 plus 6. So that's going to be 1200 plus 12 times 6, which is 72, so that would give me 1272. So I can go through and still get the value even if I don't have a calculator. Of course, with a calculator, these computations would be easier to do, but we want to make sure that you are showing the computations that you would be doing, not just punching numbers in the calculator. Okay, so a couple are left. We want to expand and hence evaluate this piece, and then, oh look, up here, we need to write using sigma notation, so we didn't quite finish out C, but we can use C and D to kind of help us out. So, for C, we need to finish writing this using a sigma notation. So for C, I might say that I have the summation. Right? I have a summation from n equals 1 to 24. My common difference was 4n, but then I would need to add 3. Right? Because that'll get me to a first term of 7. That if n equals 1, 4 times 1 plus 3. Right? And if n equals 24, 4 times 24 is 96, plus 3 is 99, and that works. Okay. So for D, we have a summation from k equals 1 to 4 of k plus 3 over k plus 2, which would be, starting at 1, that's going to be 4 over 3. If k is equal to 2, that's going to be 5 over 4. If k is equal to 3, that's going to be 6 over 5. Right? And if k is equal to 4, that's going to be 7 over, what's that going to be? 7 over 6. So I can look to see what is the common denominator that I have here. Right? And a common denominator, if I look to the prime factorizations of these. This is 3, this is 2 times 2, this is 5, and this is 3 times 2. So my prime factorization would be 3 times 4 times 5, and that would be my least or my greatest common factor, or least common multiple of these. So we say 3 times 4, that's 12, times 5, that's 60. So I'm going to have a denominator of 60. For this 4, I would need to multiply by 20. So that's going to be 4 times 20 to have my denominator. Right? For the 5, I need to multiply by, what would this be? 3 times 5. So that would be 5 times 15. For the 6, I would need to multiply by 3 times 4, so that would be 12, so that would be 6 times 12. And then plus, for the 7, I already have 1, 3, 1, 2, so I would need to multiply by 7 times 10. Right? And if I go through and do all of those summations, I have 60 in my denominator, right? And I would have, for 4 and 20, that's 80. For 5 and 15, that's 75. 6 and 12, that's 72. 7 and 10, that's 70. So really I have 70 times 3, which is 210, plus 80, that would be 290, plus 5 and 2 more, so this would give me 297 over 60. And that's a way that we could do our mathematics without a calculator. And lastly, we have a problem that says we want to insert 6 numbers between 23 and 9 so that all 8 numbers are in arithmetic sequence. So I can think about this visually and then do the mathematics. So I have 23 and then 1, 2, 3, 4, 5, 6 numbers, and then 9. And I want there to be a common difference. So what does that tell me? U sub 1 is 23. U sub 8, my 8th term, is 9. And I know that U sub 23, I know that U sub 8 is going to be U sub 1 plus my common difference 7 times. All right, what do you mean my common difference 7 times? So to go common difference once, common difference twice, 3 times, 4 times, 5 times, 6 times, and then finally it's going to be 7 times to get to that term. So what does it mean for me? That 7D is going to be my 8th term, 23, minus 9, which means 23 minus 9, that would be equal to, what, 14? So therefore, my common difference is 2. And notice, though I could have trialed and errored to do this, we do show some of the work to get to our values. And so now we know that's going to be 21, 19, 17, 15, 13, 11, and 9. But there is supporting work. There is supporting work for this. Okay? So there we are, working with some sequences and series. I thank you very much for your time.